Good morning, everyone. My name is Santiago Osorio. I am an undergraduate student at the City College of New York studying biomedical engineering, and today I'm going to be talking about my current research on benchmarking deep learning models for short exposure dark field microscopy. This work was done in collaboration with the Computational Imaging Lab here at UC Berkeley, and through the help of Dr. Laura Waller and my mentor, Sarah. At the Computational Imaging Lab, we focus on designing imaging hardware that can exceed conventional camera limits by using efficient algorithms. We integrate optics, signal processing, and machine learning for applications throughout bioimaging, defense, and industrial applications. Two example projects that frame today's work include our LED array microscope that uses a programmable LED array replacing the standard microscope lamp. This allows for one physical microscope to image in different modalities such as dark field, bright field, phase contrast, etc. Another project is our adaptive microscopy, which automatically focuses a microscope by taking a single shot, then turning on a few LEDs, and this successfully allows for the microscope to adapt to a changing sample in real time, all thanks to the power of neural networks. So what is dark field microscopy? Well, this is an imaging technique that only collects scattered light from a sample. As shown in this diagram, showing the path followed by light. In this method, the sample appears bright against a dark background. And dark field microscopy is useful because it provides a high imaging capability without using fluorescent labels, which will otherwise kill or alter living samples. This helps preserve cell viability and natural cell behavior, including movement. However, when imaging fast dynamic samples, we must use short exposures in order to avoid motion blur. In this figure, you may see how motion blur effects becomes more prominent with longer exposures, so that it increases with a longer exposure time. The problem is that when using short exposures, our images are going to have an extremely low signal-to-noise ratio, such as in the example here. The image will look grainy and dim. Even after normalizing these images based on their intensity profile, residual noise disturbs fine structural details. Some methods to address these issues include using simple denoising and brightness enhancement, but the problem with these is that they are a series of separate pre-processing steps that allow for error to build up in between. This, of course, isn't always useful when it comes to low signal-to-noise ratio situations, therefore degrading our downstream analysis capability. So here's a summary of image enhancement techniques. Some traditional methods include median or Gaussian filtering for denoising, but these methods may blur out fine details by applying an uniform smoothing over the entire image. For brightness enhancement, we may apply linear stretching or gamma correction, but these methods amplify noise, and they may clip high-intensity regions, making the image appear saturated. In recent years, deep learning has risen as a prominent approach for enhancing images because it implements an end-to-end processing approach as opposed to the separate pre-processing steps that allow for error to accumulate. Deep learning simultaneously handles denoising with brightness enhancement in a single optimization step. And depending on the dataset that we use to train our deep learning model, it may adapt to extreme low light conditions. However, this need for a sizable dataset is also one of our limitations. And if our model is not diverse enough, then it may not generalize well. Here we have a comparison of an image being reconstructed with a traditional and a deep learning pipeline. Deep learning demonstrates an impressive performance in image enhancement. We have found that there have been advances in creating deep learning models to enhance low light photographies. And these models take a extreme low light input and pair it with a reference well lit image to create a reconstruction, such as the one shown in this example. Even though these low light images are very similar to dark field short exposure images because of their low signal to noise ratio, these methods remain underexplored. So this brings us back to our goal, which is to benchmark two deep learning models originally designed for photography on short exposure dark field microscopy images. Both of the models that we used in this study were trained from scratch using identical data splits, and we evaluated quality of the images and visual preservation of fine details relative to long exposure reference images. The two deep learning models that we used in this study include the See in the Dark or SID model, which consists of a single fully convolutional network that processes RGB input directly. Our second model is the SNR-aware model that has a hybrid architecture combining a transformer and a convolutional network that are guided by the calculated signal-to-noise ratio in each region of the image. This works so that low signal-to-noise ratio regions go through the transformer and perform a long-range operation, meaning that they receive more attention when the model is training. High signal-to-noise ratio regions go through the convolutional network and perform a short-range operation. For more details about the architecture of both of these models, feel free to take a look at the two papers cited at the bottom of this slide. For this study, we used two datasets. Our simulation dataset consisted of 768 pairs of images from high SNR cell images. These images were darkened synthetically and corrupted with noise in order to mimic real-life short exposure conditions. Additionally, we acquired an experimental dataset consisting of 720 image pairs from face targets. These images were acquired with the LED array microscope shown earlier. Each image pair consists of a short exposure image paired with a long exposure image, and the pairs are smaller patches of the full-size image that are used to train our models. For a quantitative analysis, we calculated peak signal-to-noise ratio to measure the quality of the reconstructed image compared to the ground truth. Additionally, we calculated structural similarity index, which compares the image similarity between the ground truth and the reconstruction. The number 1 will indicate perfect similarity. We plotted these bar plots for both models across both datasets. The blue bar indicates the SID model performance, and the orange one indicates the performance of the SNR-aware model. As you can see, for both metrics, the SID model had an average better performance. For a qualitative analysis, we plotted the reconstructions for both datasets across both models. The top image shows the reconstructions for the simulation dataset, and the bottom image shows the reconstruction for the experimental dataset. The top row shows the reconstruction of the SID model, and the bottom row shows the reconstruction of the SNR-aware model. As you may observe, both models successfully improve the short exposure dark field microscopy image. And if we take a closer look, the SID model again outperforms the SNR-aware model by providing a better denoising, better fine detail preservation, and it also took less time to train this model. This shows that deep learning models designed for photography can successfully be adapted to dark field microscopy. We also perform an error analysis by plotting the absolute error maps for each of the reconstructions. These maps were plotted by taking the difference between the reconstructed image and the ground truth. Brighter regions in these images indicate higher reconstruction error. Again, we may observe that the SID model has lower residual error, especially at the edges of objects in the image and in fine structure detail regions. This is consistent with the structural similarity index that we calculated earlier. The SID model had a mean error of 0.6%, while the SNR-aware model had a mean error of 1.7%. Both of them are relatively low for these deep learning models. So the implications of our work are that deep learning can be successfully adapted for dark field microscopy, especially those models that were originally designed for low light photographies. Given our moderate dataset, the SID model was able to suppress noise and preserve fine details at extremely short exposures. This is consistent with prior biomedical imaging work that shows that convolutional networks have potential for enhancing images. It is possible that the SNR-aware model underperformed the SID model because transformer-based models tend to need a larger and more diverse dataset, which was one of our limitations in this study. Another limitation is that we only tested on static samples. So if we want to see how these models perform on dynamic samples and if they are able to remove motion blur, we will have to acquire a new cell dataset. Additionally, we wish to perform a direct comparison between these two deep learning models and the traditional methods that we mentioned earlier in order to ensure that they provide better results. Thank you for your attention. Now I will take any questions or suggestions. Feel free to reach out to me through my email and to connect with me on LinkedIn.